Dear all, welcome to the third lecture of the lecture series in automobile engineering. In our previous lecture, we had learned about the piston and its various components such as the piston rings, piston pin, and what their functions are and the materials that are used to make these parts. In today's lecture, we will be covering about connecting rod, crankshaft, then crank pin, which is an integral part of the crankshaft, then another shaft which is very essential for valve operation, that is camshaft, and also an introduction to the valve system. So let us move on to the connecting rod. Connecting rod is actually a very important component, and the component which converts the reciprocating motion of the piston into the rotary motion of the crankshaft. So you all have seen how the connecting rod is attached with the piston. We have a pin known as the piston pin or the wrist pin, which is hinged to the small end of the connecting rod. So we have two ends of the connecting rod basically. Here we can see the connecting rod picture, the smaller end of the connecting rod, and this is the bigger end. The smaller end of the connecting rod is attached to the piston, and the bigger end of the connecting rod is attached to the crank pin of the crankshaft. Now, usually there are many different types of connecting rods. This is one of the most commonly used type of connecting rod, where we have the big end and the small end and the big end. The small end of the connecting rod is integrated with the shank portion. So we call this portion as the shank portion, and the bigger end is divided usually into two halves. One section is integrated with the shank and the other section can be separated. We will see what are the different parts in the coming slides. So this connecting rod transfers the motion of the piston to the crankshaft, and the length of the connecting rod is reduced from 4 to 4.5 times the crank throw to 3.5 times now, in order to reduce the overall height of the engine. Now, what is crank throw? That also will be seen. Crank throw usually means that it is 1/2 of the crank revolution. Crank throw is usually the height, the 1/2 of the stroke length. The stroke length, you know, the piston travel from the top dead center to the bottom dead center, that is the stroke length. So 1/2 of that distance is known as the crank throw. Now, where there are various stresses that are acting on the connecting rod, so usually this connecting rod is made very strong compared to the piston, and connecting rod is actually made into an I section or a H section in order to reduce the weight and to have a very good strength to weight ratio. So that is why we have an I or a H section that is made for a connecting rod. The axial and bending stresses act on the connecting rod, and the axial stresses are due to the cylinder gas pressure during the combustion process, and also due to the inertia due to the reciprocating motion of the piston. So we know that the piston is connected to the small end of the connecting rod, and the crankshaft is connected to the bigger end. So the top end of the connecting rod experiences inertia force due to the reciprocating motion of the piston. And the bending stresses are acting on the connecting rod due to the centrifugal forces or effects by the motion of the crankshaft. So we have the motion of the piston that is acting or that causes a force on the smaller end, and the rotational motion of the crankshaft which causes a bending stress at the bigger end or the bigger end. So due to this, always these two stresses will be acting on the connecting rod. And as I mentioned, it is usually made into a H or I cross section to reduce the weight and to provide maximum rigidity. Now the big end of the connecting rod connects to the crank pin journal. So we call it as the crank pin journal, that are projections of the crankshaft where we attach the big end of the connecting rod. So we can see the different parts of the connecting rod here. In the smaller end, we have a small bushing that is kept, through which we insert the piston pin, and the piston pin goes through the piston bushing and it pivots the piston. So we have a pivot joint here with the piston, then the connecting rod shank, that is this portion, and the top end or the upper end of the big end is integrated with the shank. So this much portion is one single piece. Then we have two bearing shells that are coming underneath this area, that is known as the upper bearing shell and the lower bearing shell. Now the function of upper bearing shell and lower bearing shell is to provide a bearing surface where we are attaching the crank pin journal of the crankshaft. So these surfaces, these inside surfaces will be in contact with the crank pin journal of the crankshaft, and it has to be lubricated with engine oil all the times in order to reduce the friction. And the lower portion of the connecting rod, we call it as the bearing cap or the connecting rod cap, and we attach or we secure the upper portion and the lower cap by means of two bolts and nut arrangement. So we put these bolts through the holes that are drilled in the connecting rod and we tighten by means of nut. So once we are keeping this portion, or we are securing this portion within the crank pin journal, then we tighten the upper and lower portion by the bolt and nut arrangement. So these are the parts: the small end, the shank, that is the I beam, it can be I section or H section, and the bigger end which connects off the upper bearing shell, lower bearing shell, bearing cap, then the rod bolts and the rod nuts. So these are the parts of the connecting rod. Now what are the materials that are used for making connecting rod? So connecting rods, since they have to take up heavy loads, as I mentioned earlier, it has both axial and bending stresses that are acting on the connecting rod. It is made of steel alloys. Since steel is light in weight and it can also absorb high impact, so that is the reason why it is made up of steel. There are also other materials which can be used to make connecting rod, such as titanium. Titanium, it is light and a strong metal, and it is usually used in only high performance engines like in racing cars, but it is a very costly metal. So making a connecting rod for a common purpose, it is not advisable because it is very costly. In earlier days, cast iron was also used because it is cheap and it has high damping factor because it absorbs vibration, so it has a high damping factor, and it was used in low to medium sized petrol engines. But as you know, the cast iron has a lower strength when compared to alloy steels. Usually nowadays it is the steel alloys that are used for making connecting rods, and usually they are manufactured using a drop forging process. So by using drop forging process, it ensures that all the portion of the connecting rod or the entire portion remains or has a constant strength, because increased strength at any particular region will produce stress concentration, and it will in turn cause the failure of the connecting rod. So in order to prevent that, it is ensured that the connecting rod has the stress distribution equally throughout its length. Now there is a important ratio known as the L by R ratio. L by R ratio means L is the distance between the center lines of the wrist pin and the crank pin bearing. Simply telling, it is the distance between the center line of the small end and the center line of the big end. So if you are drawing two axes here, the distance between these two lines is known as the length, is known as L, and R is known as the 1/2 length of the stroke. So the ratio of this distance L and the 1/2 distance of the stroke, that is R, this L by R ratio. So L by R ratio is important because higher L by R ratio means the length of the engine frame must be large. So it is very uneconomical to produce or to manufacture large engine frames. And if L by R ratio is small, then it results in high vibrations or pulsations. So this ratio affects the pulsation, pressure pulsations, volumetric efficiency, the speed of the oil or the liquid separation, acceleration head, then the forces such as moment of inertia forces and frame size. So all these are affected by the L by R ratio. So that is why this ratio is very important. So this ratio has to be kept within a particular or a permissible limit, and common ratio range is 4:1 to 6:1. So we can keep the range as 4:1 up to 6:1. So within this range, so all these effects will be minimized. Whereas if the ratio is lesser or if it is greater, then it may cause some uneconomical challenges. Now usually in connecting roads, we may have certain passages for the flow of engine oil or the cooling oil. So we have the oil reservoir or the oil pump at the bottom, where the oil is pumped sometimes through the holes that are drilled in the connecting rod. So these holes will ensure the passage of oil from the reservoir up to the area where the pistons are located, and it provides lubrication. This is one arrangement. There are also other arrangements where the holes are drilled at the sides. So there are different arrangements of connecting rods. Now let us come to the crankshaft, which is a very important component because this is where we actually derive the power, or we take the power from. So the power that is produced by the combustion of the fuel, that is transmitted through the piston to the connecting rod, and finally it is converted to the rotary motion of the crankshaft. So the crankshaft derives its power from the connecting rod, and the connecting rod derives power from the piston. And this crankshaft is, or it will transmit the obtained power to the clutch and then to the transmission system, and the transmission system in turn transmits this power to the wheels for the movement of the vehicle. So we all know what is the function of the clutch is. We will be learning it in the later stages of our class. And transmission system, the gear system using which the different gears are used for the different riding conditions. The crankshaft assembly consists of the crankshaft and the bearings that are integrated with the crankshaft. There may be flywheel which is used to store energy for rotating the crankshaft during the idle strokes. Then it may have vibration dampener to reduce the vibrations produced due to the rotary motion of the piston. And it also has a sprocket or a gear to drive the camshaft. Camshaft is a shaft which is used to control the opening and closing of the inlet and exhaust valve that we'll be seeing later on in the slides. And also oil seals at the front and the rear. So all these are the different parts of the crankshaft assembly, and all these are usually integrated together. So you can see the different parts of the crankshaft mentioned here. So this is the shape of the crankshaft. So if we start from the left side, we have the flywheel end where the flywheel is attached. Flywheel is usually a bigger wheel of a comparatively larger weight, which is used to store energy, kinetic energy, so that the energy that is produced during the power stroke is stored in the flywheel, and it is used to rotate the crankshafts for the next 3 idle strokes. So idle strokes is the suction stroke, the compression stroke, and the exhaust stroke. So these 3 strokes do not produce any energy and they consume energy. So in order to work during those idle strokes, the crankshaft needs energy, and this energy is utilized from the stored energy in the flywheel. Then we have the thrust bearing, and this is the main bearing. So if you take the crankshaft, we have multiple main journals which support the crankshaft. So this is the first one, second, third, fourth, and fifth. So this journals which are coming at the axis of the crankshaft, they are known as the main journal bearings. And the function of main journal bearings is, the first function is to circulate oil to the crank pins that are located at the ends of this main journal, and also the other main function is to support or to give stability to the crankshaft, because most of the weights are supported by the main journals. Okay, now the next projection here is the crank pin, and crank pin is the region where the larger end of the connecting rod is attached. So we have seen the connecting rod where it has a smaller end and a bigger end or the larger end. So the big end of the connecting rod is attached to the crank pin, and this crank pin is offset at a small distance from the center of the crankshaft. So if you draw an axis through the center of the crankshaft, the axis of this crank pin is lying at a small distance from the center of this crankshaft. That means it is offset by a small distance. And this offset distance gives or tells you the amount of the stroke length that is happening. It is also mentioned as the crank throw that is happening. And the surface, the edge surface of the crank pin, we call it as the crank web. You can see here that holes are drilled at the crank web surface. So from main journals, in main journals there will be small drilled oil holes, and oil is carried through rotation. So when the crankshaft rotates due to the centrifugal force, the oil is transferred through the holes that are drilled in the crank web part, and it is flowing to the other parts of the crankshaft. So that is how we ensure that the crankshaft is fully lubricated while it is being rotated. So the oil that is being pumped or it is being circulated, it comes in between the interface of the connecting rod and the crank pin, and it lubricates this area so that the friction is not developed during the working of the engine. So there should not be any friction between the bigger end of the connecting rod and the crank pin. It should rotate freely. So that is why lubrication is provided. And we also have certain counterweights that are attached in order to balance the unbalanced forces during the rotation of the crankshaft. So the main parts include journals, that is the main journal bearings, and the counterweights. The counterweights are used to balance the rotational motion and to balance the unbalanced forces. Main journals, as I mentioned, supports the mass of the crankshaft, and the connecting rod journals support the connecting rod and offset from the main journals. Counterweights add momentum to the crankshaft and helps the engine to run smoothly. So you can see here the picture of the crankshaft, the main journals, and also the counterweights. They are machined into specific profile shapes. You can see here counterweights, they are used to balance the unbalanced masses. We can see the original picture of how the crankshaft looks like. We can see the holes here. So these portions or these areas which are lying in the axis of the crankshaft, these are the main journal bearings. So main journal bearings, they have holes. Also the crank pin journals also have holes drilled, and there are also holes drilled in the crank web. This is known as the crank web. So at the sides you can see there will be holes drilled so that oil flows through all these journals. Now if you look at the arrangement here, this crankshaft is for a 4-cylinder engine. We'll have 4 pistons that are mounted like this, 2 pistons and the next 2 pistons, so they will be symmetrical. That is how it operates, and the angles at which these pistons are mounted, they will be different. So the crankshaft rotates about the axis of the main bearings, and crank pins are the journals for the connecting rod big end bearings. And we also saw what is a crank throw, that is the distance between the axis of the main journal and the crank pin center. So this distance, that is the main journal, if you take the axis here, the distance between the axis drawn through the main journal and the crank pin journal. So this small distance is known as the crank throw. So crank throw is usually equal to 1/2 of the stroke length or the engine stroke, and that is the ratio. We learned the ratio L/R. So R here denotes the crank throw, and it determines the crankshaft turning effort. And we also saw that the function of the holes that are drilled in the main journals, that is to supply oil to provide lubrication. And main bearings are lubricated from oil galleries. Oil galleries simply means they are small areas where the oil is stored once we pour in the engine oil. So in the cylinder block there are certain areas known as oil galleries which supply oil, or where the oil is contained. So crankshaft should be, or it usually experiences very heavy loading. The loading from the forces that is coming from the piston is transmitted to the crankshaft through the connecting rod, and a lot of stresses are acting on the crankshaft. Therefore, the material used for crankshaft should be resistant to bending, because a lot of bending forces are acting on the crankshaft. And since it experiences a cyclic loading, it experiences both bending as well as tensile stresses simultaneously. So that is known as a cyclic stress. So crankshaft usually undergoes cyclic stress, and whenever a material undergoes a cyclic stress for a long period of time, there is a chance that a fatigue failure can occur. Fatigue failure means the failure of the material due to cyclic loading, and the material fails prematurely, and it fails much before than that is expected. So that is known as fatigue failure. So crankshaft can undergo fatigue failure due to cyclic loading. So therefore, the material used for crankshaft should have excellent fatigue resistance, and it should be lightweight so that the moment of inertia can be reduced and motion can be transmitted more efficiently. Since the temperature inside the engine also remains high, the coefficient of thermal expansion should be less so that it does not change its dimension at different temperatures. And also it should be easily machinable so that it can be machined into complex shapes. You can see here that the shape of the crankshaft is a bit complex in nature. So in order to machine this complex shape, it should be, the material used for making the crankshaft should be easily machinable. And unnecessary stresses should not be developed. So what are the materials that are used for manufacturing crankshafts? Crankshafts are manufactured from steel. Usually the common material used for manufacturing crankshaft is steel. And the process of manufacturing crankshaft, it is either by forging or by casting. Both these processes, that is forging and casting, have their own advantages as well as disadvantages. The forging, the forging process, it reduces or it deforms the grain structure of the material and it makes it much more stronger. So that is the advantage of forging. So forged crankshafts, they are much more stronger than the crankshafts that are made by casting process. But forging is a bit expensive, so forged crankshafts are more expensive. And it makes the material very dense in nature, because you see that the grain structure of the material that undergoes forging, it becomes very dense structure because the grain structure is deformed and the grains come very closer to each other and reaches a stage where further deformation of the material cannot take place. So it is very dense and tough. And the crankshafts which are made by casting, they are comparatively not much stronger, but they are very easy to make because the casting process, we can make complex shapes very easily. So that is the advantage of casting. The strength will be less, but complex shapes can be made. So whenever we are applying or whenever we are using a crankshaft for very heavy loads, heavy load operations, the forged crankshafts are preferred because it is very strong and very dense. For low to medium load conditions, cast crankshafts are considered because heavy loads will not be applicable and it can be also manufactured easily and it is less costly. So crankshafts which are made by casting, they are usually made of steel, modular cast iron or by malleable iron. Next we come to another shaft mechanism that is equally important, that is known as the camshaft. Camshafts usually are shafts on which we have a multiple number of cams that are machined on it, and the function of these cams is to operate the inlet and exhaust valves of the engine. And you might have seen the operation of cams when you have done the thermal engineering lab. If you have performed the experiment on valve timing diagram, you can see that in the lab there is a cut section of a single cylinder 4-stroke Kirloskar diesel engine on which you have performed the valve timing diagram experiment. So in that setup you can see the camshaft, the rotation of the camshaft, and also how the cam is operating the opening and closing of the valves. So camshaft is a rotating shaft. It is made up of metal and it contains the cam. And you might have also learned about the cam profile. The cams convert the rotary motion of the camshaft into the reciprocating motion of the valves. You can see the animation here, how the cams are coming into contact with the valve mechanism and it is helping in the opening and closing of the valve mechanism. The pointed structure of the cam is called the cam lobe. So whenever the cam lobe comes into contact with the follower is the portion where the cam comes into contact. So it pushes the follower down, and since the valves are spring loaded, it pushes the valves down and opens the valve. And once the lobe portion of the cam passes away due to the spring pressure, the valves will automatically close. And this is the actual setup in the engine. Usually for the inlet valves and the exhaust valves, there will be separate camshafts. One camshaft is entirely for operating the inlet valves, and another camshaft is entirely for operating the exhaust valves. And these two, or the camshafts, are usually run at half the rotational speed of the crankshaft. So if crankshaft is rotating at say around 1500 rpm, the speed of the camshaft is adjusted to run at 750 rpm. Usually that is the ratio. Camshafts usually run at 1/2 the rotational speed of the crankshaft. And there are several mechanisms by which we can transmit the motion of the crankshaft to the camshaft. This is one such mechanism. This is known as the timing belt. There is a chain and sprocket mechanism. So using this timing belt, we are timing the rotational motion of the camshaft and thereby timing the opening and closing of these valves. So these valves cannot open and close as we like. There should be a specific timing for opening and closing each of these valves. Especially in multi-cylinder engines, opening and closing of the valves are very important. So in order to time it perfectly, proper adjustments have to be made on the camshafts and proper timing has to be arranged such that the cams come into contact with the valves at that point of time and it opens and closes at the appropriate time. So if you look at the cam, this is the cam profile. You have the base circle, which is almost semicircle in shape, and you have the pointed structure, which is known as the cam lobe. And there are two flank surfaces, slanting surfaces. One is known as the opening flank and another is known as the closing flank. So whenever this cam rotates and the opening flank region contacts the follower, you can see here, suppose this is rotating in a clockwise direction. So now the opening flank area is in contact with the follower area, the follower top area. So when it rotates, it pushes down the follower. If it is spring loaded, it will push down the follower or the tappet and it opens the valve. And once it reaches the tip of this nose or the lobe section, the lift of the valve is the highest. That means the valve will be open at the maximum condition when it is the contact of the when the contact is occurring at this tip. So the cam probe, when it is in contact with the follower, there is a maximum lift of the valve. And finally, after that, the closing flank area comes into contact with the follower, and due to the spring loaded mechanism, the valve closes automatically. This camshaft is usually forged from alloy steel, or it can also be cast from malleable cast iron or grey cast iron. Case hardening process, which is a surface hardening, is done on the different cams. You can see here, for the different cam surfaces, because it is always coming into contact with a metallic portion, there is a probability that wear and tear will occur. So in order to reduce in order to minimize the wear and tear, the outer surface or the contacting surface of the cams are usually case hardened or surface hardened by different methods. The material used for camshaft, it is usually chilled grey cast iron and it is produced by casting. So camshafts usually they are available as billets. Billets in the sense they are cylindrical rods. Then on we have to make them, we have to manufacture the shapes by various machining processes. Other than chilled grey cast iron, other materials that are used for manufacturing camshafts are hardenable iron, spheroidal graphite or SG cast iron, and chilled chrome cast iron is used in high performance engines. Nitriding steel again similarly, it is more costly and again used in high performance engines. And at the end of this video I'll be showing how the crankshaft and camshafts are manufactured. So you can see clearly in that video which are the machining processes used to manufacture camshaft. Next we move on to valves. Valves are usually the inlet valves and the exhaust valves. They are used to admit in the air fuel mixture or air in the case of diesel engine, and to let out the exhaust gases from the engine we make use of the exhaust valve. So there are two valves, inlet valve and exhaust valve. The three categories of valves, broadly if you are looking at valves, the three categories are poppet valve, sleeve valve and rotary valves. In IC engines usually we make use of the first category, that is the poppet valve. They are universally used in automobile engines. And these valves are operated mechanically by means of the camshaft mechanism. Camshaft and the valve arrangement, all this together, they form the valve actuating mechanism. Now, why is it called a poppet valve? So this is the poppet valve, the valves that are usually noticed in IC engines. You might have seen while doing the experiment the shape of the poppet valve. Poppet valve, it is also known as the mushroom valve because of its shape. It resembles a mushroom because it has a stem that is having a thinner cross section and a head which is having a larger diameter. So a lower diameter stem and a larger diameter head. And because of its popping up and down, opening and closing, that is why it is known as the poppet valve. The poppet valves are lifted from its seats by cams. So usually these valves they rest in metallic seats in the engine cylinder. So in the engine cylinders there will be holes that are drilled, and on these holes we press fit some metallic seats, and on these metallic seats these valves command rest. So the seats are used to make a airtight arrangement. The rate of valve opening and closing depends on the profile of the cam, that is the cam outline, size and shape of the cam and the follower mechanism. The valves should open and close quickly, and it should also remain for the greatest possible time. So that is how for the inlet valve it can admit in more air fuel mixture or the required air fuel mixture, and the exhaust valve, it can let out the maximum exhaust gases if the valves remain open for the greatest possible time. The poppet valves, why are these poppet valves used in IC engines and why not any other type of valves? Because it has many other advantages mentioned here. It is very simple in construction. These are the different parts mentioned. The flat portion with a larger diameter is known as the head. After the head, there is a small area cut out, that is the margin, and a conical face, and this conical face again reduces in diameter, and the reduced diameter is known as the stem. And there is also a slot that is cut in, you can see here, where we load one end of the spring mechanism. So in order to prevent the spring from moving out, it is this cutout area retains the spring. That is why it is known as spring retainer lock groove, and then the tip of the valve. So the construction is very simple. It is self-centering. It means opening and closing. After it is closing, there won't be any problems. It will automatically close, and it will close with the center. And it is free to rotate about the stem. We will see why this free to rotate is very important in the engine. And maintenance of sealing efficiency is greater, because the sealing efficiency means once the valve is closed, the inlet, at the inlet valve, air should not get in, and at the exhaust valve, the air or the exhaust gases or the air that is remaining inside the engine should not go out. So high sealing efficiency is needed to produce the required compression ratio and also to maintain the efficiency. So all this can be achieved easily by means of poppet valves, and that is why it is preferred. Now there are certain interesting things which you may not have noticed. That is, usually the inlet valves are found to be larger in size than the exhaust valves, or the exhaust valves are made smaller than the inlet valves. There are certain reasons. First is, in inlet valves, the speed of incoming air fuel mixture is less than the exhaust gas that is leaving under pressure. Even though air fuel mixture is taken in, the speed comparatively, when compared with speed of exhaust gas, the inlet condition speed is less. So in order to admit more air fuel mixture in the case of petrol engine, or more air in the case of diesel engine, a little bit more area, larger area is required. So that is why, one of the reason why inlet valve is made larger. The second reason is that the exhaust valves are more temperature is associated with the exhaust valves, because usually the hot gases leave through the exhaust valve, and always there is a chance that the exhaust valves are remaining at a very hot condition compared with the inlet valves. So since the temperature is more at the exhaust region or exhaust valves, if larger material is used, it takes more time for cooling. The use of smaller exhaust valves ensure that little amount of material is needed. Compared to the inlet valves, there is only a small size difference. Even then, the exhaust valves will cool much faster because the material is lesser. We need to keep the exhaust valves or we need to cool the exhaust valves soon before the next cycle, because if sufficient high temperature or more than sufficient high temperature is maintained at the exhaust valve side, it may fail eventually. So in order to avoid that, we need to ensure that the exhaust valves are cooled intermittently between the cycles. So that is another reason why the exhaust valves are smaller in size when compared to the inlet valves. Then the next reason is the density of exhaust gases is comparatively high and it easily flows through the smaller opening. And the shorter path of heat flow and reduced thermal loading. So that is another reason, reduced thermal loading. So we can, if you are making it in a smaller size, exhaust valves in a smaller size, it reduces the thermal effects. So due to these reasons, we can see that in an engine, if we see, the inlet valves are comparatively larger when compared with the exhaust valves. Sizes usually are in this range. Inlet valves and exhaust valves are 45% and 38%. So there is a difference of 7% size between the inlet and exhaust valves. 45% and 38% size of the cylinder bore, that is the inside diameter of the cylinder. So both these valves are at these percentage sizes of the cylinder bore. That is the ratio that is maintained. And the stem diameter of exhaust valve is 10 to 15% greater than that of the inlet valve. So here it is mentioned inlet valves are larger in the sense the head are larger, head portion is larger, and the stem diameter of the exhaust valve is greater, because as I mentioned, thermal loading occurs due to the high temperature in the exhaust valves, and due to this high temperature there is a chance that the valves will eventually fail due to the loading condition. So in order to prevent that, if we increase the stem diameter, we can prevent the damage to a certain extent. That is why the stem diameter of exhaust valve is made larger. The stem diameter does not actually affect the cooling process, because you can see in the coming slides, most high temperature is experienced at the valve head, and as we move along through the valve from the valve head to the tip, we can see that temperature decreases. So the temperature at the valve head is larger when compared with the valve stem. So even if we increase the material in the valve stem, it does not really or greatly affect the cooling process. The valve lift should be at least 25% of the valve head diameter. So usually that is a ratio, or the ratio that is maintained. If the valve lift is less, that means if the valve does not open sufficiently, the volumetric efficiency will be decreased, because first thing is proper intake will not be there. Sufficient air fuel mixture will not be entering into the engine cylinder, and also sufficient exhaust will not be exhausted out of the cylinder. So this will affect the volumetric efficiency. If the valve lift is more, then the inertia of the valve actuating mechanism will result in excessive noise and wear. So even if the valve lift is greater than that is expected, then the valve actuating mechanism will result in, the inertia will result in excessive noise and wear, and also it will also affect the volumetric efficiency. So it should be maintained within a proper permissible limit. That is mentioned here, that is the 25% of valve head diameter. And the valve phase angle, usually the valves are not kept straight. If you noticed in the engine, these valves are inclined at an angle. It is kept at a small angle, or it is bored and fixed at a small angle in the engine cylinder. So this inclination of this angle is around 30 to 40. It can range from 30 up to 45 degrees. Smaller phase angle results in greater valve opening, but it also results in the poor sealing, because we cannot control the proper sealing of the valve, and results in poor sealing and decrease of volumetric efficiency. These valves, as I mentioned earlier, it will come and rest on valve seat, and valve seat is usually machined on the cylinder head, and it is the surface on which the valve comes and rests when it is closed. You can see here the different types of valves, valve seating. This is the conical arrangement where conical valves are used, and this is the flat seated valve where we do not have a conical section. It is a flat arrangement. The valve operating temperatures, as we mentioned, the valves are subjected to high temperatures, but as we progress along the different parts of the valve, there is a temperature gradient. Different parts of the valve experience different temperatures. The head of the valve is the region where the maximum temperature is experienced by the burning of gases. And this valve seats should not undergo any corrosion, any chemical corrosion due to the high temperature, and the valve stems also should not wear rapidly. Now, at high temperatures, there is a phenomenon known as the corrosion fatigue due to high temperatures and stresses that is experienced. So during operations, sometimes a valve may break at a distance below the head, a small distance below the head where the temperature is maximum, and this is due to corrosion fatigue. And corrosion fatigue, again, it occurs due to repeated mechanical stress. So as I mentioned, there is cyclical stress that is happening, and also high temperatures and the chemical corrosive action of the exhaust gases. The exhaust gas contains many compounds of sulfur and nitrogen which can corrode the surfaces at high temperatures. So due to this corrosive action and cyclic stresses, the corrosion fatigue failure can occur, due to which the valves may break after a point of time. Mostly this failure, valve failure, is found at the exhaust valves, because exhaust valves are the valves which experience higher temperatures. The exhaust valves are subjected to cyclic stresses due to the spring loading. The springs are loaded on the valves in order to operate these valves. Closing and opening is controlled by the spring loading mechanism. And due to the creep conditions due to high temperatures and corrosive environment of the gases. So usually valve failure occurs at the exhaust valves. Inlet valve failures are very rare because temperatures do not rise very high, and again corrosive exhaust gases are also not coming into contact with the inlet valves. So inlet valves are safe, and exhaust valves experience the failure due to corrosion fatigue. And the temperatures may reach very high due to or during the full load conditions of the engine. So high as much as 1475, it can go almost up to 2000 or 2500 degree Fahrenheit. So such high temperatures, these valves must withstand at these high temperatures. And as engine speed increases, the valve temperature or the temperature inside the engine also increases. And the valve temperatures depend on heat caused by combustion and the temperature of the exhaust gases. So both these are causes of raising the temperatures of the valve. You can see here the temperature profiles, or how the temperature distribution occurs at different areas of the valve. The highest temperature occurs, these all are mentioned in degrees Celsius, 750 to 800 degrees Celsius, that is occurring at the center of the valve head. This is the case of an exhaust valve. So at the center of the valve head, usually the temperature ranges come to around 750 to 800. Tip of the valve heads, it is comparatively lower temperature. And as we proceed towards the center, you can see temperature increases. Again, temperature increases and then it decreases. So you can see multiple temperature gradients or changes in temperature along the cross section of the valve. So due to this, you can see the highest temperature being developed in this area, that is the valve, the region where the valve stem comes to meet with the valve head, this conical section. So this is the area where frequently failure occurs. So if the valve breaks, it will break around this area. And due to these high temperatures, the exhaust valve should be made of materials which can withstand high temperatures as well as the stress conditions at higher temperatures. So it should have high strength and hardness to resist tensile loading. Tensile loading occurs due to the spring loading. It should withstand high hot strength. It should have high hot strength. Fatigue and creep resistance should be there. Corrosion resistance should be there. Coefficient of thermal expansion should be less. And higher thermal conductivity for better heat dissipation. That is, it must cool very fast. So these are the requirements of the material with which the valves should be, the exhaust valves should be made. And the valve materials that is basically used comes into three different types or three different alloys: silicon chromium steel, austenitic chromium nickel steel, and mnemonic nickel base alloys. In olden days, silicon chromium steels were used as valve materials. The composition is shown here: 0.8% carbon, 0.4 manganese, 1.3 nickel, 2% silicon, 20% of chromium, and the balance is iron. So chromium and iron are the major components. Chromium is used to increase or to improve the hot hardness. That means the resistance at higher temperatures is increased by addition of chromium. Silicon and chromium steel was used in earlier days. After that, austenitic chromium nickel steels were used. The percentage of carbon 0.25%, 1.5% manganese, silicon 1%, 12% nickel, and 21% of chromium. So the content of nickel increased, and this was made in an austenitic condition. So this was used sometime after the silicon chromium steels were introduced. And finally, the mnemonic nickel base alloys, which are used in heavy duty engines, they are used for very high temperature operations. It is not usually used in low and medium duty engines or in normal conditions, only for special purposes. It has a composition. The carbon content, as you can see, is very low, 0.05% carbon, manganese, silicon, chromium. Again, it has major component 20%, and 67.65% of nickel. So instead of iron, nickel has become the major constituent. So this is mainly used, or neonic nickel based alloys are mainly used as valve materials only for very heavy duty purposes. And the inlet valves, since they are operating at 773 Kelvin, it is a low temperature because only a small temperature rise is observed at the inlet valve. Usually ambient temperature air or air fuel mixture is taken in, so there is no chance of high temperature occurring at the inlet valve. So special alloy materials are not used in case of inlet valves. So usually we make use of silicon chromium steel. The composition shown here, 0.4% carbon, 8% chromium and 87.1% iron. So chromium content is again less because high temperature strength is not much needed for inlet valves, because high temperature does not occur at the inlet condition. You can see here the valve seat that was mentioned earlier. So it is a ring shaped structure that is press fit into the hole that is drilled in the engine cylinder. So valves come and sit on these valve seats. Then there are different types of valve seats. It can be integral or separate inserts. Integral seats are directly machined on the cylinder head, and separate inserts means they are different components like this which are inserted and fixed into the cylinder head on the holes that are drilled in the cylinder head. You can see here the arrangement. This is the inlet valve and this is the exhaust valve. Here integral valve seat or valve seats are machined on the surface of the cylinder head itself, and here we have the valve seat that is press fit into the hole that is drilled. Usually press fit valve seats are used in case of exhaust valves where high temperatures are noticed. In normal conditions, at inlet conditions, press fit valve seats are not required. Then another component of the valve mechanism is the valve spring. Valve spring, we make use of usually a helical spring to give a spring action to the opening and closing of the valve. And spring is when the cam operates on the tappet or the follower, the spring is compressed, so it is subjected to compressive loads, and the spring is ground flat at each end. So ends of the springs are ground to a flat profile to ensure even pressure distribution, and coil ends are placed diametrically opposite to avoid bending tendency. So that means if one end is starting from a region, so the other end of the spring will be at the diametrically opposite end. And valves, again, they are made from high grade spring steel wire, usual high grade spring steel wires. Chromium, vanadium steel or hard drawn carbon steels are used as the materials. You can see the arrangement of the valve spring. So this is the tappet mechanism. which pushes down the valve. So the pushing of the valve will compress the spring, and when the cam profile or the lobe passes the tappet, due to the spring action, the valve again closes. We also have a component known as valve rotators, which are used to rotate the valves automatically. So I had mentioned very earlier that we need to keep the temperatures uniform across the cross section of the valve head. So in order to do that, in order to cool the valves, particularly the exhaust valve, we need to cool it before the next cycle. So in order to make this possible, we make use of valve rotators. So valve rotators, what it does is it automatically rotates the valve after every exhaust cycle, exhaust strokes. So after one cycle is over, exhaust is over, the valve is rotated at a particular angle or a particular degree before the next cycle occurs. So this will ensure that the heat is not concentrated at one particular area of the valve. So at each time, different regions will experience heat, so that cooling also can take place quickly and it does not fail very soon. Premature failing does not occur due to the concentration of heat at one particular place. Different mechanisms are used for valve rotation. Different mechanisms are there. You need not study in detail about the different valve rotating mechanisms. Different mechanisms are there to rotate the valves automatically. And valve rotation also ensures that it equalizes the temperature and keeps the valve seating clean, because especially the exhaust valve, when the exhaust gases are passing through the exhaust valve, the exhaust gases will contain carbon and other deposits, and it will accumulate at the valve seating as well as the valve head, etc. So after some time it will affect the valve closing. It will not ensure proper closing of the valves. Some leakage might be there, due to which the efficiencies will decrease. So due to this, and in order to prevent this, if the valve is rotated, it will ensure that the dust or the deposit particles are thrown away, or it does not deposit on the surface of the valves, and it always keeps the valves clean. Then there are valve guides. Valve guides are small through holes, or we can say concentric cylinders, through which it is a bushing actually, through which the valve stems pass. And there is a very little clearance between the valve stem and the valve guide. So the valve stem is kept or pushed through this hole in the valve guide. It is actually a bushing, and this ensures that the valve stem does not come into contact with the cylinder head, and it prevents wearing of the valve stem. The valve guides are usually made of cast iron, and they are force fitted in the cylinder head. So in this diagram we can see the valve guide that is fit inside the cylinder head, and through which the valve stem is inserted. So the valve stem moves up and down inside the valve guide. And longer valve guide keeps the valve head cooler. So the valve guide has also the function of reducing the valve temperatures, because it ensures that the upper portion, that is the stem region, is isolated from the high temperature. It is insulated from the high temperature due to combustion. So it ensures that the other portion of the valves are maintained at a sufficiently lower temperature. Then we have the push rod mechanism, which you have seen in the valve timing diagram experiment which you conducted in your lab. The push rod is a long, slender cylindrical rod which transmits the valve lifter reciprocating motion to the rocker arm. You can see here, this is the arrangement that you might have seen in the single cylinder 4-stroke Kirloskar diesel engine in which you have performed the valve timing diagram experiment. So you have the camshaft here. So the camshaft, when it comes and contacts the valve lifter, it will lift the push rod that is attached to the valve lifter, and the push rod in turn is bolted to a lever arm, and this lever arm, one end will be lifted and the other end will be lowered, and thereby this end will push the valve open, push it downwards, and the valve will open. So that is the function of the push rod, that is to transmit the motion from the valve lifter to the rocker arm. This arm is the rocker arm. And push rod is made up of usually carbon manganese steel and has a Brenner hardness number of 250. So this push rod usually undergoes a rocking mechanism, and due to this, the push rod and the valve lifter, such components should be made of or should have high sufficient strength so that the failure does not occur. Since you know that the crankshaft may run at 1500 to 2000, maybe 3000 or 4000 rpm, the camshaft also will have half the rotational speed of the crankshaft. So as crankshaft speed, rotation speed increases, camshaft speed also increases, and the rate at which the push rod has to operate, the speed also increases. So due to this, sudden rocking motions may occur frequently at the push rod and other mechanisms, and therefore all these parts should be made of high strength material. Then we have the rocker arm and the rocker shaft. The rocker shaft is the shaft that is passing through the center of this rocker arm, and it is acting as the lever. It acts as the pivot. Acts as the pivot, and the rocker arm acts as the lever mechanism. So one shaft that is passing through the center of the rocker arm is the rocker shaft. Now, a rocker arm can be made of forged steel or cast iron, and rocker shafts are made from hollow steel tubing. The composition is given here, and the shaft is case hardened. Case hardened means the hardening is done only at the surface, and it is placed in between the pair of rocker arms like this. So we will see about the valve and the different valve actuating mechanisms in our next lecture, and right now I will show you how the crankshafts and camshafts are manufactured. Kindly view this video. This is the video of how the connecting rod is connected to the crankshaft. You can first view this video.
What I want to talk about right now is how the up and down motion of the pistons in their cylinder bores is translated into the rotation of the crankshaft. Now here is a piston. The wrist pin connects the piston to the connecting rod. The connecting rod is assembled on the crankshaft in two halves. It is split and bolted. It has these alignment pins which go into these holes. Now, The main bearings, which are these 5, simply revolve around their own axes. The crank pins are offset and they describe circles of their own. To attach this to the crankshaft, we would add some pre-lube, because plain bearing engines, everything has to be pre-lubed to make up for the several seconds it takes for the oil pump to send fresh oil around to every place that it's needed. So this would go onto the crank pin. The connecting rod cap would be slid into place, and connecting rod cap bolts would be installed. These bolts are responsible for making sure that the piston obeys orders at top dead center. It doesn't keep going and smash all the valves flat. Instead, it is obediently dragged by the crankshaft down on either its suction or its power stroke. So these bolts have to be remarkably strong. The metallurgy in connecting rod bolts is usually of the best. Once the bolts are in place and they've been torqued to the correct preload, when the crankshaft revolves, the piston rises and falls. So the straight line motion of the piston up and down in the cylinder bore is by means of the wrist pin, the hinge point, and the connecting rod transformed into rotary motion at the crankshaft. Now, to anyone who's ever worked with gas turbines or jet engines, this just seems hopelessly medieval. The idea of pumping air with pistons. But gas turbines have been tried in automobiles, buses, and trucks, and where are they now? The advantage of piston engines is that their speed is easily controlled and also their load. So, until the fabled electric revolution is upon us, we're stuck with back and forth motion of pistons translated into rotary motion at the crankshaft by means of the hinge connecting rod.
You can now see how the crankshaft and camshafts are manufactured. So you have seen how the crankshaft and camshafts are manufactured. In our next lecture, we will see how the valves are operated. There are different valve actuating mechanisms, different valve arrangements that we will see in the next lecture. So kindly go through this video completely and contact me in case of any doubts. So thank you for today's session.